Scene script. Imagine finding a needle in a haystack, but the needle is invisible. That's how complexometric titration works in identifying ions in a solution. Welcome to the world of complexometric titration, a method that's as intricate as its name. It's a technique used in analytical chemistry, the science that helps us understand what matters are composed of. Specifically, complexometric titration is employed to determine the concentration of an unknown metal ion in a solution. Picture it as a kind of detective work, except instead of solving a crime, it's figuring out how much of a certain metal ion is present in a solution. But how does it do that? Well, it's all about creating a complex. In this case, a complex is a molecule that's formed from the reaction of a metal ion with a ligand, a molecule that binds to another, usually larger molecule. When the right amount of ligand is added to the solution, it will react with all of the metal ions, forming a complex. By observing this reaction, we can determine the concentration of the metal ion. What's more, complexometric titration isn't just a cool party trick for chemists. It has real-world applications that impact our daily lives. It's used in the pharmaceutical industry to ensure the correct dosage of medicines. It's employed in water treatment plants to monitor the levels of metal ions in our water supply. Even the food industry uses it to check the mineral content in our food, so the next time you take a sip of water, remember there's a good chance that complexometric titration was involved in ensuring its safety. Or when you take that vitamin supplement, know that it's this method that helps ensure you're getting the right amount of minerals. Complexometric titration, an invisible needle finder, isn't it fascinating? Ever been in a crowded room and found yourself drawn to a particular person? That's what happens in a solution during complex formation. Imagine you're in a room filled with people. Some you know, some you don't, some you're indifferent to, and some you're extremely attracted to. This attraction is similar to the forces that drive complex formation in a solution. When a metal ion finds a ligand it's attracted to, they form a bond. This is the heart of complex formation. But how can you tell how strong this bond is? Enter stability constants. In our social analogy, it's like the measure of how likely you are to keep a conversation going with someone you're attracted to compared to someone you're not. In chemistry, the stability constant or formation constant is a measure of the strength of the bond between the metal ion and the ligand. A higher stability constant means a stronger bond. Now, why does this matter in complexometric titration? Well, in the same way that you might navigate a crowded room trying to find the most interesting person to talk to, a titrant in a solution is looking for the metal ion with which it can form the most stable complex. This is why EDTA, a common titrant, is so useful. It forms very stable complexes with many different metal ions. In a complexometric titration, we gradually add the titrant to the solution until all the metal ions have formed complexes. The point at which this happens is the end point of the titration. Knowing the stability constants helps us predict and understand when this end point will be reached. Just like in a room full of people, the most stable relationships in a solution are the ones that last. Chelates, not to be confused with the cheese, are the superheroes of complexometric titration. Let's dive into the world of Chelates. Picture a crab, its pincers reaching out and gripping onto things. This is essentially what chelates do on a microscopic level. They are molecules that have the capability to form several bonds with a single metal ion, and in doing so, they grip onto the metal, creating a stable structure. This process is pivotal in complexometric titration as it allows for the accurate measurement of metal ions in a solution. Now, there's a special agent in this world of chelates, and its name is ETA, or to give it its full title, ethylenediamine tetraacetic acid. Quite a mouthful, isn't it? EDTA is a chelating agent that's commonly used in titrations due to its ability to bind with various metal ions. It's like the Swiss Army knife of chelating agents, versatile and reliable. But how do we know when EDTA has done its job? That's where Metal-EDTA titration curves come into play. Picture a heart monitor, each beep representing a heartbeat. A Metal-EDTA titration curve is somewhat similar. It records the heartbeat of the reaction, with each point on the curve representing a moment in the titration process. As we add EDTA to our solution, it starts to bind with the metal ions, forming a chelate. This is reflected in the curve, with the points rising as more and more chelates are formed. Then, as all the metal ions are bound and no more chelates can be formed, the curve levels off. This point where the curve flattens is known as the end point, and it tells us that the titration is complete. So there you have it, a whirlwind tour of Chelates and Metal-EDTA titration curves. As you can see, these chelates, with their ability to grip onto metal ions and help us measure them accurately, are the unsung heroes of complexometric titration. Chelates, the superheroes we never knew we needed. In the world of complexometric titration, metal indicators are the traffic lights guiding the reaction. They act as the watchful eyes, alerting us when the reaction has reached its endpoint, the precise moment when all of the analyte has reacted. Think of them as the umpires of a cricket match declaring the end of an over. Now, let's delve into the world of metal indicators. These are special compounds that form colored complexes with metal ions. When the color changes, that's our signal that the analyte has fully reacted. It's like an artist's palette where each color signifies a different stage of the reaction. The most common type of metal indicator used in complexometric titration is areochrome black tea. It's the superstar of the show, known for its ability to form a wine-red complex with most metal ions. When the reaction is complete, the solution changes color from red to blue, signaling the end of the reaction. It's like a dramatic color-changing light show, all happening in a tiny reaction vessel. Now, let's tune into the melodies of complexometric titration. Each type of titration is like a different genre of music, each with its own unique rhythm and flow. Direct titration is the pop music of titration. It's straightforward and simple. The analyte is reacted directly with a complexing agent, and the end point is detected by a metal indicator. On the other hand, back titration is the jazz of the complexometric world. It's a little more complex, involving an excess of complexing agent added to the analyte, and the remaining complexing agent is then titrated. Indirect titration is like classical music, elegant and methodical. Here, the analyte reacts with a complexing agent, forming a precipitate. The precipitate is then dissolved and titrated. And finally, we have the substitution titration, the rock and roll of titration, where a known complex is substituted by another ligand. From traffic lights to music genres, complexometric titration is a world full of analogies. As we journey through the fascinating world of complexometric titration, we realize it's not just about invisible needles and traffic lights. It's an intricate dance of molecules and ions, a symphony of reactions and stability constants that underpin much of our understanding and application of chemistry. Let's take a moment to reflect on what we've learned today. We started with the unveiling of complexometric titration, a technique that allows us to measure the concentration of an unknown metal ion in a solution. It's like a detective story, where the detective is the EDTA molecule and the culprit is the metal ion hiding in the solution. We then delved into the world of complexes and stability constants, where we learned that not all complexes are created equal. Some are more stable than others, and this stability is quantified by the stability constant. It's as if each complex is a building and the stability constant is the architect's blueprint, dictating how sturdy the building will be. From there, we moved on to chelates and Metal-EDTA titration curves. We saw how chelates are like the handcuffs that the EDTA detective uses to capture the metal ion culprit. The titration curve, on the other hand, is the detective's case file, charting the course of the investigation and providing valuable information about the unknown metal ion. Next, we explored metal indicators and the different types of complexometric titrations. The metal indicators act like traffic lights, signaling when the titration is complete. The different types of titrations, meanwhile, are like different investigation techniques that the EDTA detective can use, depending on the nature of the case. Understanding complexometric titration is not just for the sake of knowledge. It has real-world implications, from water treatment to medicine, and from environmental monitoring to industrial processes. It's like a hidden language spoken by chemicals and understood by chemists that helps us make sense of the world around us. Complexometric titration, a symphony of molecules, ions, and reactions. Subscribe for more, because you won't find me later.